Unit 4 Fields Notes. Let's see if we can go through at least a little bit of this today to hopefully give you guys a little bit of a better understanding of what's going on here. We're going to be looking at gravitational fields, electric fields, and magnetic fields. We're all well familiar with the force of gravity and what it's equal to. Each planet has a different gravitational field. So as you can see over here, Earth's, as we see it, is 9.81, Mars is 3.71. Etc. One of the things that will be maybe a little bit more unique this unit is the fact that we're going to be drawing field lines, and they can be represented in the following way. Always perpendicular to whatever the object that is shown, and there's going to be a specific strength associated with it due to the number of lines actually, and so there's going to be a specific line density. And the weaker the field, as you can see here on Mars, it's a lot weaker. There's less field lines than there is here on Earth. And that's going to be one way to determine where a field is a little bit stronger than others. And that's going to be true for gravitational fields, the electric ones, and magnetic as well. We briefly mentioned this in the past too, the difference between mass and weight. Mass being basically the total amount of matter, and it really doesn't change based on your location. Your mass is your mass. The amount of matter you possess maintains the same amount, albeit if you eat something that might change a little bit, but you get the idea. Weight will change, and we gave a handout on that on the elevator questions, and it's a good idea to make sure to look over that as well to develop a deeper understanding of what it looks like for apparent weight and when you're accelerating either upwards or downwards and how that actually affects your overall apparent weight. Here, weight is measured in newtons, mass is always going to be measured in kilograms. This activity, unfortunately, we're unable to do, although if you do have a scale at home, you could use that. You don't have to use your own body weight. You could choose some random object from your house, and you could attempt to put that on the spring scale to determine whatever the mass might be. You could always estimate it ahead of time too, and then determine what it is afterwards. Your weight obviously can be just calculated based on whatever your mass is multiplied by 9.8. So mass does not change, well, at least not easily. You could either add matter or remove it. There's also some stuff out there where they talk about if you're going really, really fast, like incredibly fast, closer to the speed of light, your mass might change. But we're not going to get into that. Today, we're going to be looking at how do you actually change the weight, and that's pretty easily done actually. So what you're going to attempt to do, again, if you have the balance scale at home, you're going to maybe attempt to double the weight of whatever mass that you chose to do. What are you going to need to do in order for that to happen? Quadruple it. Good luck doing that. I'm not sure if that's going to be possible depending upon the weight that you chose. Anyways, give that a try. This was one big question though that I would love for you guys to think about at least a little bit. How heavy could you make this mass if you had as strong of a spring spell as you possibly wanted, an infinite reach with unlimited reach, unlimited speed? It's nice food for thought. Anyways, moving forward beyond that, now, how in the world would you maybe make your mass lighter? Is it possible for you to make it half its original weight? What are you going to have to do in order for that to happen? You might have to lift your scale off of the floor. At some point, obviously, you have some of the answers here too. How light could you actually make it? Well, if you dropped it fast enough, it's not going to have any weight particularly, right? It's going to be dropping at the same speed of gravity or faster. We went over this in class a little bit. Is it possible to have a negative weight? Well, really not for a person, but we pose that question, what about a helium balloon that actually rises in the Earth's atmosphere? The summary, mass for all intents and purposes is going to always stay the same. It's always going to be measured in kilograms, while weight is in newtons. How do you actually increase your weight? Well, it's going to have to either accelerate upwards. So that's the big thing. To decrease your weight, you're going to have to accelerate downwards. How do we get some of these examples here? Well, again, how do you get weight is just force gravity, mass times gravity. That's what we did. We just went 88 times 9.8. Now, if he's hopping on a roller coaster that's accelerating upwards, what's his total mass? The thing that I always do, start off with my force diagram right over here, my free body diagram. I've documented my force of gravity, my normal force, and even where is it accelerating, upwards or downwards. Afterwards, I go to my FNet and I say, okay, well, I have a force normal. That's the force that's going to be pushing upwards, minus my force of gravity, and it's going to all equal my FNet total, which is also MA. Rearrange it for finding your normal force, because again, your normal force is whatever your parent weight is going to be. Plug in your values and solve. The bottom one over here, Todd falls off the roller coaster, lands on Mars, which has a gravitational acceleration of 3.711 meters per second squared. What is his apparent weight? Well, in this case over here, your force normal is equal to your force gravity, because he's just falling, free falling. It's going to be his mass multiplied by the acceleration due to gravity on that planet. And that's where we're going to get 326.6. And as you can see, there's 4 significant figures in the question, and so I've included 4 significant figures in my answer as well. For this one over here, not a bad idea to actually take a look at this video. It's not very long. Most of these videos are only about 10 minutes long. So take a look at Electric Fields Crash Course Physics number 26. And when I went through this too, I just paused it after each rule, and then I was able to write down what that particular rule was. The main highlights of that is that we mentioned this first one before. Field lines have to be tangent to whatever the field direction is. So for gravity, gravity is coming towards the Earth, and so the lines as you saw them before way back over here were tangent to the Earth's surface, and they were coming inwards, right? They were coming towards the Earth there. We mentioned rule number 2 already as well. Actually, the greater the line density, the greater the magnitude. So the more lines, the greater the field actually is. And the lines always start from positively charged objects and end on negatively charged objects. So from a positively charged object, we haven't mentioned this yet, but the arrows are going to be facing outwards for positively charged objects, and negatively charged objects, you're going to have the arrows facing inwards there. And lastly, lines must never cross. We'll leave it at that for today, I think. And then we'll begin talking about this come Monday, electric fields here. Thanks.